A car slows for a pedestrian at a crosswalk. Beneath it, 4 patches of tire meet the road. Together, they are not much larger than a few open hands. In that brief stop, each patch must flatten, grip, warm, and recover before the wheel turns again. The black surface looks solid and simple. It is neither. A tread block contains long molecules, reinforcing particles, protective chemicals, and carefully controlled links. Beneath it sit other rubber compounds, steel, textile, and trapped air. Each part carries a different piece of the same demand. Rubber became civilization scale only when that recoverable material joined air, reinforcement, factories, roads, labor, and rules. The tire did not create modern mobility alone, but without a reliable place for machine and road to meet, speed, freight, and everyday travel would take a very different form. That makes the contact patch personal. It shapes how your vehicle stops. Its condition depends on pressure, age, heat, and maintenance. People tap the latex, mix the compounds, build the tire, repair the road, and manage what wears away. Every trip depends on their work, and every trip leaves some material behind. Rubber did not enter history as a European invention. Indigenous societies in the Americas had already collected latex and shaped elastic, water-resistant objects. They understood a living material drawn from plants long before European manufacturers tried to force it into shoes, cloth, hoses, and factory goods. The raw substance was remarkable. Pull it, and it could stretch. Release it, and much of its shape returned. It resisted water. It could join flexible surfaces that leather, wood, and metal could not replace. Yet its behavior changed with heat, cold, time, and handling. Early rubber goods could become sticky in warm weather. In cold conditions, they could stiffen. A useful shape might creep or distort. Manufacturers saw enormous promise, followed by spoiled products and angry customers. Elasticity was already there. Dependability was not. That difference matters. A rubber ball can be a curiosity, while a tire must repeat the same demanding action for thousands of kilometers. It must bend without staying bent. It must hold together while warm. It must survive oxygen, sunlight, water, impacts, and constant flexing. 19th century experimenters spent years mixing rubber with powders, solvents, metals, heat, and sulfur. Charles Goodyear became the best-known name in the United States. Thomas Hancock developed and patented related work in Britain. The familiar story of one lucky accident hides a longer, contested process of experimentation. Controlled heating with sulfur changed the industrial future of rubber. The treatment made useful properties more stable across a wider range of conditions. It did not create a perfect substance. It created a material that engineers could begin to formulate, shape, test, and reproduce. Then another idea changed the job rubber was asked to do. Instead of placing a hard band around a wheel, designers enclosed air inside a flexible structure. By the 1890s, pneumatic bicycle tires were making rides smoother and faster. Cyclists wanted better roads, and the new tires soon moved from bicycles to automobiles. The air carried load, but air alone was useless. It needed a flexible container that could survive bending and stay attached to the wheel. Rubber had become stable enough to serve that system. The next challenge was making it strong, consistent, and durable enough for machines moving farther and faster. To understand that change, imagine a bowl of very long, cooked noodles. They twist around one another, and they can change shape in countless ways. Natural rubber begins with a similarly tangled population of long molecules, although the real network is far smaller and more crowded. Polyisoprene is the long chain molecule that makes up most natural rubber. When the material stretches, many chain sections become more aligned. When the force disappears, thermal motion helps the chains return toward a larger range of tangled arrangements. That is the basic source of rubber's spring-like recovery. But loose chains can slowly move past one another. Given heat, force, and time, the material can flow or keep part of a new shape. A useful tire compound needs the chains to move locally without escaping the whole network. A crosslink is a connection that keeps neighboring chains in one network. Sulfur-based curing creates many such connections. They are not identical staples placed at even intervals. Real networks contain several link structures, loops, loose ends, entanglements, and regions shaped by mixing and cure history. With too little control, the material can remain weak or unstable. Change the network, and stiffness, heat resistance, fatigue, and aging also change. Tire makers are not seeking the largest possible number of links. They are tuning how far different compounds can move and how reliably they return. Natural rubber has another useful response under strong stretch. It is called strain-induced crystallization. It means stretch chain segments briefly form small ordered regions. Those regions help the material resist further deformation, then largely disappear when the load is removed. This does not turn a rolling tire into solid crystal. The response depends on temperature, formulation, speed, previous loading, and the shape of damage. It helps explain why natural rubber remains valuable in demanding, fatigue-sensitive uses. It does not make cracks or poor maintenance harmless. The polymer network is still only part of a tread compound. Fine carbon black aggregates can reinforce rubber by creating an enormous, complicated interface with the chains. They change stiffness, strength, wear, processing, and resistance to sunlight. Modern compounds may also use silica and specialized linking chemistry. There is no single ingredient that produces every desired property. Grip requires deformation at the road. That deformation also turns some motion into heat. Resistance to wear can conflict with traction under another condition. Cold, rain, load, speed, and pavement move the compromise again. So the contact patch is not a passive footprint. Tread blocks enter, bend, press against texture, and leave. The carcass changes shape around them. Some energy returns to the moving vehicle. Some becomes heat. Some material separates as wear. Recovery must begin before the same region comes around again. The process that stabilizes rubber is called vulcanization. In simple terms, heat in a cure system build the cross-linked network. In practice, sulfur may form different kinds of links, while accelerators and activators control how the reaction proceeds. The useful result depends on formulation, temperature, pressure, and time. Vulcanization solved one problem, then revealed many others. Pure cured rubber could not meet every demand of a modern tire. A tread needs abrasion resistance and grip. A sidewall must flex and weather. An inner liner must slow air loss. The bead must transfer force where tire meets rim. That is why a tire factory does not begin with one black recipe. Workers and machines prepare separate compounds for separate jobs. Natural and synthetic rubbers may be blended. Fillers, oils, protective chemicals, and cure ingredients are mixed under carefully managed heat and mechanical force. Timing matters because the material must remain workable before final cure. Compounds are extruded or rolled into tread, sidewall, liner, and thin bonding layers. Rubber is also pressed around textile cords or steel. Each operation creates an intermediate part that another operation must place accurately. On a building drum, the tire starts as an uncured assembly called a green tire. An inner liner goes down first in a common radial design. Carcass plies extend towards strong bead bundles. Sidewalls are added. Steel belts, optional cap plies, and the tread form a second assembly around the crown. The body expands into the belt and tread. Rollers press the components together. Their uncured tack helps them stay positioned, but the structure is not finished. A bladder then pushes the green tire into a heated mold. Pressure shapes the object while the compounds cure and bond. What leaves the mold is not a rubber ring. It is a pressure-containing composite designed to deform in controlled ways. Air pressure, carcass tension, belt geometry, beads, and several compounds share the load. The visible tread is only the road-facing edge of that system. The historical path was just as layered. Sulfur treatment made rubber goods more dependable. Pneumatic bicycle tires showed what air and flexible material could do together. Better fillers, cords, compounds, radial structures, factory control, testing, and road design extended that performance. No single workshop produced the modern tire in one leap. The breakthrough was the growing ability to divide conflicting jobs among materials and reunite them in one repeatable object. That required chemistry, skilled hands, machines, standards, and a supply chain reaching far beyond the factory wall. For a cyclist on a rough 19th-century street, the change was physical. Air-filled tires softened repeated shocks and made faster travel more tolerable. Their popularity helped widen the bicycle market. Cyclists also became advocates for smoother roads, creating pressure that later motorists inherited. Automobiles asked far more of the same basic idea. Vehicles became heavier and faster. Engines delivered more power. Brakes and steering placed new forces through the contact patch. Tire makers responded with new compounds, cords, belt structures, tread patterns, and methods for making them consistently. Reliable tires relaxed a constraint on where machines could travel. Trucks were not tied to rails. Buses could follow changing routes. Farm machines entered fields. Emergency vehicles, construction equipment, and aircraft all depended on specialized versions of the flexible road interface. But rubber did not build this world by itself. Steel made vehicles and reinforcement. Petroleum supplied fuel and synthetic polymers. Factories reduced cost. Credit expanded purchasing. Governments paved roads, wrote traffic rules, and chose where infrastructure would go. Maintenance networks kept vehicles moving. As demand grew, the material connected distant landscapes. Rubber trees originated in the Amazon, where wild extraction fed an international boom. Production later shifted toward cultivated trees in Southeast Asia. Colonial institutions, plantation capital, botanical transfer, disease management, trade, and smallholder farming reshaped supply. That history cannot be reduced to trees replacing trees. Natural forest, monoculture plantation, and mixed agroforestry are different systems. Nor did every producer share one experience. Plantation workers, independent smallholders, managers, states, and traders faced different risks and held very different power. The human work begins with a precise cut. A tapper opens latex vessels in the bark without cutting so deeply that the tree is badly damaged. Latex collects slowly, often during early working hours. The task repeats across seasons shaped by rain, disease, prices, and the condition of each tree. The material then passes through collection and processing before it can become consistent industrial feedstock. That distance hides labor from the driver. A person checking tire pressure sees a finished black surface, not the tree. Cut, cup, coagulation, grading, shipping, mixing, and inspection behind it. Global dependence became impossible to ignore during World War II. When the United States lost access to most Southeast Asian supply, rubber was rationed and conserved. Government, universities, oil companies, and tire makers shared patents and built a vast program around general-purpose synthetic rubber. Factories scaled with remarkable speed, but substitution had limits. Synthetic rubber changed the industry permanently without erasing natural rubber. Different polymers offered different advantages. Tire makers learned to blend them and assign them to particular regions instead of waiting for one universal replacement. That mixed system remains with us. Natural rubber is still strategically important in demanding applications, while synthetic elastomers connect mobility to petroleum. Geographic concentration makes weather, disease, land policy, labor, shipping, and geopolitics part of what appears to be an ordinary tire purchase. The result is a civilization-scale dependency built around replacement. Tread wears, tires age, casings fail inspection, fleets plan downtime, shops maintain pressure and alignment. Road agencies manage surfaces and drainage. Mobility works because millions of people continually replace, repair, monitor, and govern the interface. Now, return to the contact patch. Grip exists because rubber and road deform against one another. That interaction cannot happen without friction. Over time, pieces of tread and pavement separate. The tire becomes lighter by an amount too small to notice after one trip, but the loss never truly disappears. Tire and road wear particles are not one clean powder. They contain polymer, filler, minerals from pavement, and many additives. Some remain near the road, some enter the air. Rain carries others into drains, soil, streams, and sediment. Their size, chemistry, and path continue changing after release. Even measuring them is difficult. Black particles are hard to distinguish from soot and road material. Laboratory preparation can damage the rubber being counted. Estimates change with traffic, braking, speed, vehicle, tire, pavement, weather, and method. A dramatic global number can hide more than it explains. The hazards also differ. Researchers have linked particular transformed tire chemicals to severe effects in sensitive fish. That evidence is important. It does not mean every particle has the same toxicity or follows the same route into every organism. Compound, dose, weathering, place, and exposure remain essential. The cost begins long before the road. Most natural rubber grows in tropical regions, much of it in Southeast Asia. High-resolution satellite research has tied substantial forest loss there to rubber expansion. Yet a mixed smallholding, an old plantation, and newly cleared natural forest cannot share one environmental label. Livelihood and harm can occupy the same landscape. Rubber supports many smallholders and workers. Plantation tasks also bring real safety and health concerns. The evidence differs by country and labor system, so there is no need to invent one tragic worker. A controlled tapping cut and a carried bucket already reveal skilled, repetitive labor. Manufacturing extends the footprint through synthetic rubber, carbon black, silica, oils, chemicals, metals, textiles, energy, and industrial emissions. Tire life then depends on maintenance. Poor inflation and alignment can increase heat, wear, fuel use, and risk. The driver becomes part of the material system. At the end, the network that made rubber dependable becomes a barrier. A cured tire cannot simply be melted and cast like clean metal. Crosslinks hold the polymer, while steel, textile, fillers, coatings, dirt, and several compounds resist separation. Some sound casings can be retreaded, preserving far more of the original structure. Other tires become ground rubber, construction material, fuel, oil and char, or experimental recovered feedstock. Calling every route recycling erases how much function, energy, and material quality each one actually preserves. The tire therefore carries a difficult bargain. It makes friction controllable enough to move and stop. That same friction spreads material through the environment. Its durable network survives repeated use. That same network prevents easy return to the form from which it began. There is no single green tire waiting to solve every part of that bargain. Longer life can reduce replacement, but a harder low-wear tread must still grip in rain and cold. Lower rolling resistance can save energy, but safety, durability, noise, and handling remain part of the same design. The first improvements may be unglamorous. Correct pressure, alignment, rotation, inspection, and repair help tires do their intended work. Fleet retreading can preserve a qualified casing instead of discarding the whole composite. Road and stormwater design can reduce how much wear reaches sensitive waterways. Material recovery needs clearer language. Grinding changes size, not the cross-linked network. Pyrolysis breaks material into different outputs. Devulcanization tries to cut selected links while keeping more long chains intact. That selectivity is difficult, and recovered material must still prove consistent performance in a demanding new compound. Researchers are also looking beyond one tree. Guayule, a desert shrub, can produce natural rubber with a similar polymer backbone. It may diversify supply and reduce dependence on one tropical crop. But demonstration tires do not settle farming yield, water, land, extraction, quality, cost, or industrial scale. Plantation systems can change too. Better traceability can identify forest conversion. Agroforestry can mix rubber with other vegetation and incomes in some settings. Worker protections can improve tasks that remain essential. None of these steps makes every product harmless, and none works without institutions that reward the improvement. The deeper opportunity is to stop asking one material to carry the whole solution. Tire makers can change compounds and construction. Vehicle designers can reduce unnecessary mass. Drivers and fleets can maintain pressure. Cities can manage runoff. Producers can protect forests and workers. Recovery systems can preserve the highest useful function available. The pedestrian reaches the other side. The brake releases, and the interrupted wheel completes its turn. The contact patch lifts from the road. Its rubber network recovers, carrying most of its shape forward and leaving an almost invisible trace behind. Inside that motion is a tropical tree, a careful cut. Tangled chains, sulfur links, reinforcing particles, tire builders, steel cords, and trapped air. It also carries paved roads, maintenance decisions, and a waste system still struggling to reverse what curing made permanent. Rubber did not put the world on wheels by itself. It gave wheels a recoverable meeting place with an imperfect surface. Human systems scaled that ability, distributed its benefits, and displaced its costs. Once the contact patch becomes visible, mobility looks different. It is no longer a machine floating over the road. It is a repeated material negotiation between grip and loss, durability and recovery, distance and responsibility. How carefully are we willing to manage that meeting place?